and somehow he kept black hair, and I didn't. I don't know why. But
nobody made me director of anything, so.
So it's a pleasure to have Markus here. He's going to talk about blowing the dark matter wind.
Hi, I understand there was a completely different title in the talk. I don't know if that was my fault or not, but anyway, this is what I'm talking about. This is work in progress. So with an undergraduate student, Hannah Day Daliu, who's a postdoc at Maryland, and Yue Zhao at University of Utah. Before I get started, I just want to say that for me, coming here is very much connected with Eduardo Ponton. For those of you who don't know, he was actually my PhD student. So for a time, we saw each other pretty much every day. We worked together, and I felt very close with him. And then, of course, as these things happen, your best students go away and they fly off. And he certainly did. But boy, I really never thought that I wouldn't see him again, even after he was going through all that he went through. And so anyway, that's very much on my mind these days. And I'll look forward to talking with those others of you who maybe knew him more recently at Monday's symposium. So I'm going to talk about dark matter. And so just a very, very general introduction. Dark matter is a subject where we have many ideas, many theoretical models, but no actual clue as to the identity of dark matter. We really know very, very little. And if we really step away from our theoretical prejudice, dark matter could have a mass as low as 10 to the minus 34 eV. That's basically so that its wavelength fits inside a galaxy. And it could go even well beyond the Planck scale. They could be large macroscopic objects, as far as we know. Is it 22?
This is the size of the universe.
Oh, that's the size of the universe. I'm sorry. I copied this from somebody else's slide, so I copied it wrong. Okay, yeah, this is supposed to be 1 over the size of the galaxy. I'm not going to be down. I'm going to be up here, but yes, thank you. All right, this is going to really set the tone for the quality of this talk, as you can see. Right? Hopefully I got this right. The WIMPs are generally particle-like dark matter, or the most commonly looked for between, let's say, a GeV and a TeV, maybe a little lower, maybe a little higher. I'm going to be focusing on this range below about 10 eV, because in that range, if dark matter can be a light bosonic field, it essentially behaves as a coherent field, okay? And the point is that when we're faced with something like this, and if we're faced with the fact that our theoretical prejudices recently haven't been turned out so well, right? We did not find supersymmetry or composite Higgs or Technicolor at the LHC, and we have not detected WIMPs. Perhaps we should be more modest and just explore the full range of possibilities as well as we can. And that's the sort of spirit in which I'm doing what I'm doing. Of course, any given strategy, we have to search in some region. And so I said, I'm going to be focusing on this region here. Okay? So in this region, as I said, dark matter today is more like a field. So just to review, this is very standard things, but just to review, the way you produce the dark matter is by the misalignment mechanism. Okay, so this dark matter has a mass, which will be very small, and if the temperature is above the mass, then the field will be basically frozen by Hubble friction. As the temperature drops below this mass, it starts to oscillate, and that produces a coherent dark matter field today. So today it's something like an oscillatory field that's coherent, and the dark matter density is just given by the energy stored in this field. So you can think of it either as a classical field that's oscillating like this, or you can think of it as a Bose condensate of many, many dark matter particles at rest. These are two equivalent pictures for the same thing.
So thinking of this dark matter as always non-relativistic.
You can think of it as particles. You can think of it as being, yes, ultra non-relativistic. Yeah, at rest. Of course, what gravitationally, this wave starts to become deformed and overdense regions start moving around, and so those overdense regions move around very much the way that ordinary dark matter particles would move around. But yes, okay? Okay? So now, if I'm going to look for these things, I have to just assume some coupling to the standard model. This is purely phenomenological. So what we do is, motivated by effective field theory ideas, we expect that the leading couplings will be to some low-dimension standard model coupling with given quantum numbers, okay? So if we just start writing down low-dimensional operators in the standard model, we can write down the Higgs mass operator, that's at dimension 2. There's a whole lot of dimension 4 operators and so on. And each one of these operators coupling to the dark matter field corresponds to some kind of portal. So I'm going to be focusing on the very, very lowest dimension operator I can have, the Higgs portal. And so the usual operator that people would write down for the Higgs portal would be a linear coupling of phi to h dagger h. This has been much explored, so we're going to assume that this operator is not present, which can easily happen, for example, if there's a Z2 symmetry under which phi is odd, in which case the leading operator would be a coupling of phi squared to the Higgs coupling, okay? So this is just, these are some relatively arbitrary choices. The motivation is going to be that this is going to give rise to some new signals, okay? So this type of model has been discussed before. I don't know if it was given this name, but it should be called the Z2 Higgs portal. But I'm going to talk about some new signals that this kind of model has for dark matter detection, okay? Okay, so since we have a coherent field, right, we can think of the coherent field as a Bose condensate of particles, but these particles individually carry practically no energy and momentum. So what we're going to be looking for are coherent effects of the whole field. Namely, we're going to be looking at forces that this dark matter exerts on ordinary matter, okay, on detectors. And so at very low energies, you know, ultimately we went through this Higgs portal, but at very low energies, the most important coupling of this field is to nucleons, okay? So that has a coupling of 1 over F, and you can estimate what 1 over F is based on what we know from QCD, and it's related to this parameter epsilon by some formula like this, okay? I don't care very much about this, the details of this, because I'm just going to use F as my phenomenological parameter, okay? So you can do something a little more accurate than this, but this is a reasonable estimate for how it's related to epsilon, okay? So now let me compare this model to the model where we replace this phi squared by phi. This is the model which is much more studied, and this is what's usually called the Higgs portal dark matter model, okay? So if you have just a phi here, then you get very strong constraints from just forces mediated by this phi, right? This phi is ultralight, it's below an EV, so you have very strong constraints from equivalence principle forces. But now in this model, this turns into a loop diagram, so it's very, very suppressed, okay? So if you check, these provide very stringent bounds on the previous model, but this provides practically no constraint at all compared to the ones I'll talk about a little bit later. On the other hand, scattering is enhanced because in the phi model where I just had phi here, I would have to use the interaction twice to scatter, right? And remember, this interaction is going to be extremely weak. So scattering would be second order in this small coupling here if I had the linear model. But now that I have squared, this thing is just linear in my small parameter. And so these scattering effects are going to be enhanced. And this is why we're going to get new signals in this, out of this kind of model. Okay? Okay. Okay, so what are the constraints? There are some stringent constraints on this model. One of them is just from star cooling. So just like any time you have a light field that couples to the standard model, you have this type of constraint. Nucleons can just scatter and make your light particle, and that can cool supernova and red giants and everything else, okay? And so that gives you a bound on this 1 over F coupling that's quite stringent. It's comparable. This is sort of familiar from the axion particle. It's not very different because it basically, the important point is it's a dimension 5 interaction, right? Okay? And that was worked out a long time ago. Another very important constraint that's kind of a little bit more interesting is nucleosynthesis. So this dark matter was presumably there during nucleosynthesis. And during nucleosynthesis, there was a much larger dark matter density, right? And of course, if you look through nucleosynthesis, it was biggest, the dark matter density was biggest at the very beginning of nucleosynthesis, okay? So it turns out the dominant effect of this thing on nucleosynthesis is that it changes the proton-neutron mass difference, right? Because I have this coupling phi squared times the nucleon mass, but that actually changes the proton-neutron mass difference a little bit, right? Because the proton, okay? And so that effect then, propagates through nucleosynthesis, and you get a bound that goes like this, that depends on the mass of phi.
Sorry, but phi is frozen, right? But the mass is 10 to the minus 6 electron volts. So
That's right, but it was still bigger.
it's not a particle. It's not a particle.
No, this is just a number. You're right. It's a number that's redshifting, but it's still changing the proton-neutron mass difference, and so it's affecting the helium-4 abundance.
So the field is contributing to the energy density.
Yes. Well, it's really contributing to the proton-neutron mass difference, because nucleosynthesis is very, very sensitive. If you change the proton-neutron mass difference, you just totally mess things up. Okay, so this is the thing that nucleosynthesis is sort of the most sensitive to, and I'm trying to argue that because this is biggest at the beginning, if you just change the initial condition for this, and then you can just basically propagate it through analytically, and you can find this constraint.
But it also changes the energy density, the expansion rate.
Yes, it changes a lot of other things too, but they turn out all to be much smaller. Okay, and that's actually validated by full numerical calculations. So this was an analytic estimate. It turns out to be spot on. I'll show you in just the next slide.
For the mass range you're interested in, the field phi is oscillating or not?
At BBN, no. So the temperature is MeV, right? The temperature is of order MeV, and the phi mass is less than EV or 10 EV, so it's frozen.
With the mass, not the temperature.
I'm sorry, you're right. It's Hubble.
The action is much lighter
Yes.
than 1 GeV.
I think you're right. I think it actually oscillates. I think it oscillates, and I think actually, yeah, but I think you can average over the
So
oscillations.
the action oscillates around GeV and it's much lighter because of the action.
Yeah,
MEV,
yeah, I think that's right. I'm sorry. Yes, I think you're right. Right. This is not my work, but yes, I think I agree. So here, let me just show you what these constraints look like, okay? So here is that constraint. Oh, I don't know what happened here. Oh, no, that's correct. I think it's correct. No, somehow this axis, yeah, I think it's correct. Yeah, okay. Okay, so here was the sort of star cooling, and you can also check that the force tests and things like that have a much more complicated jagged line, but they all live up here, okay? And then here are the nucleosynthesis lines, and the dashed lines are the analytic ones, and the solid lines are actual complete numerical code, blah, 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 done by TTU. Okay, so I don't think this is published, but that just shows that you can really, especially on a log-log plot, you can just believe the analytic constraints. And here are some other constraints that won't matter very much for us. You'll see later, we're going to be up here, okay? But there are some superradiance constraints, some pulsar constraints. There are even other constraints that we found that I'm not going to talk about that kind of live in here, okay? But you can basically say this is the allowed region, okay? All right? Okay, so now I want to explain the title of this title of the talk. So what we're going to look at is we're going to focus on experiments that average over the dark matter oscillations, okay? So for very, very light dark matter, maybe back down here, okay, the mass is so light that these oscillations are actually something you can track in an experiment, okay? And that actually, for this model, for the linear model, that gives you interesting constraints. For this model, however, those constraints are too weak for the reason that I sort of roughly explained. So what we're going to focus on instead are larger masses so that the dark matter field is oscillating so rapidly that we just average over the oscillations, okay? In that case, what happens is that, and actually what we have to, there's a little bit of a subtlety, the time scale we have to average over is not 1 over the mass of the dark matter, which is 1 over the frequency, because actually there's a coherence time, right? What happens is that there's an average motion of the dark matter, which is the fact that the galactic halo is at rest in the galactic frame, and then the matter is churning around through it, right? So we're out here somewhere, so we know just from how we're rotating around the galaxy that on average the dark matter wind is coming from a known direction, okay? But what's happening on this timescale T coherence is that the instantaneous direction and magnitude is changing, okay? So it's only when we average over this coherence time that we see an average dark matter wind, okay? So we're going to be looking at experiments that average over these times, and you can see that if the mass is near an EV, this is a very short time scale. So any kind of normal macroscopic force experiment will just not see anything on this short of a time scale, okay? All right? And this kind of signal, we're not the first people to consider this kind of signal. There was an interesting paper by Yanagida and collaborators that looked at exactly this kind of signal, but I'm not going to say anything more about this, this paper because I'm a polite person. No, they just did the calculations are just completely wrong, okay? But they had the idea to look at this kind of effect, okay? All right? I guess I'm not so polite. Okay. All right, so let's see how big these forces could possibly be, okay? Well, the most optimistic estimate you could possibly make is that every single dark matter particle that hits my object bounces off, okay? I absolutely could not get a bigger force than that, right? So all I do is I know how much momentum density there is in the dark matter wind, and I just assume that all of it is transferred to the object, right? That's insanely optimistic. And so even then, you see that you get an incredibly tiny force. Notice that the force is proportional to the area, okay, right? So it depends on the, but if I take a centimeter size object, which is the kind of thing I might be interested in for a mechanical force experiment, I'm talking about 10 to the minus 14 newtons, okay? And if you're familiar with these kinds of experiments, this is actually an interesting number. This is right around where they are, as we'll see, okay? And the remarkable thing is that we can actually saturate this bound. You may think this is, surely we can't have strongly interacting dark matter. But we can, it turns out, okay? So let me try to convince you of that, okay? So let me think about how does this phi field propagate in matter, okay? Well, if I look at this thing from the point of view of phi, I see that whenever I have a nucleon number density, I'm getting a correction to the mass of phi, right? And so the correction is proportional to the number density of nucleons. Okay, so I can just, so one thing you notice, and I'm assuming that the sign of this is always positive. Okay, actually the phenomenology is very different if it's negative. And so I'm phenomenology driven, not model driven, so I'm interested in this phenomenology. So it gives you a positive correction to the mass, I'm assuming, okay, of mass squared of phi, okay? But you see, if that mass gets too big, that means that the phi field cannot propagate inside matter. This is just like the Meissner effect for photons, right? And so if you look at the k vector in matter, it is the k vector in vacuum minus this mass shift, right? This is just because I have to match the frequency. I get this formula here. And if that k squared is negative, then I have an exponential suppression rather than propagation inside of matter. And that happens for this kind of range of parameter space. If 1 over f is big enough compared to m phi squared, then I have this exponential suppression, okay? Now so this is the sort of dark matter Meissner effect. That's still not enough to get complete reflection because then if this is satisfied, then I have some exponential fall off inside the material, but my target has to be big enough, right? Has to be bigger than the exponential fall off length, than the skin depth in the case of the Meissner thing, right? A very, very thin metal, sufficiently thin metal would not reflect. And so the radius of the material, the target, has to be bigger than 1 over k inside matter, and that tells you that 1 over f has to be bigger than something that depends on the radius. Okay, so let's see what this looks like on the plot. Here's the same plot, here's the allowed region, and if I want the Meissner effect, I have this light blue region right here, it's above, right? And then if I also want, I should have written it here, this is for 1 centimeter, so this is 1 centimeter is bigger 1 over k matter, I get this purple region up here. So remember, this is a log-log plot, so this is not very big, but this is several orders of magnitude in both parameters, right? Okay, and so in this purple region here, I actually have complete reflection, and this bound that I gave there is actually saturated, okay? All right, so what are the features of this force? So I just want to think about the general features of this force to think about whether we can detect it or not, okay? So because we're going to be averaging over these incoherent oscillations or incoherent whatever changes, the force effectively has a constant magnitude and direction in the galactic reference frame. So I rate that a thumbs up. It may sound this is bad because it's a DC force, but there are very simple ways of turning a DC force into an AC force, namely just rotate your experiment. So all the equivalence violating tests, they are looking for a static force, for example, from looking for a static equivalence principle violating force due to the Earth, for example, but they rotate their experiment to turn that into an AC thing, and then they get a signal at a known frequency. So having a signal that's a DC with a, it's DC and with a fixed direction is actually very good for detection. Okay, it's a known way to deal with that. Okay. The other thing that's important here is that the force is proportional to the area, right? This is very good because this maximally violates the equivalence principle, right? Unless you accidentally make your two masses exactly the same size and shape, right? So it's very easy to get the thing to violate the equivalence principle. The other types of forces that come from, for example, well, anyway, a lot of these dark matter forces approximately satisfy the equivalence principle and makes them harder to detect. Okay, so that gets a thumbs up. On the other hand, the thing that's bad is what's also good about this is also what's very bad about this, because if I do have this maximal force, it means that that matter, just ordinary matter, shields the dark matter wind. So I better put my, I can't have any shielding, or I can't have too much shielding anyway around my experiment, okay? And that makes it harder, so that gets a big thumbs down. That's the challenge in this, for seeing this kind of force, okay? So what we want is we want very sensitive force measurement with minimal shielding, okay? And so what we want are satellite tests of the equivalence principle, okay? Which fortunately nature has provided us, or experimentalists, okay? And the one that we have, the premier satellite test of the equivalence principle is called MICROSCOPE. This is an actual experiment. So this thing actually already flew, okay? And so the way it works is it has two test masses in these cylinders that are, of course, deeply embedded in here. And their sensitive axis is the cylinders to move this way, I believe. And so it's an orbit around the Earth, and also the satellite is rotating. So again, they've turned an AC signal. For them, they're looking for equivalence principle violating forces from the Earth. We would have some constant force in some random direction, so they would have to reanalyze things. But basically, they have a sensitivity of acceleration of around 10 to the minus 13 meters per second squared. That's pretty remarkably small. Like you could figure out how long it would take you to get up to the speed that grass grows or something with an acceleration like that. Anyway, it's a tiny acceleration. Their mass is not, a third of a kilogram, and their size is order 3 centimeters. So, it's in the ballpark of this force that I told you about. The problem with this thing is that these guys are, as you see, they're 3 centimeters, okay? But this is not 3 centimeters, right? This is like a meter. And I don't know exactly how thick everything is here, but you can see there's a lot of stuff around these little cylinders here, okay? And so we don't, this is not a truly accurate, so what we did is this, for the target, we used the numbers that I showed you there. We approximated the size of the target because they tell us that very precisely. And then what we did is we just gave you the bounds for various amounts of shielding. So if there's 0 shielding around it, that would be some idealized experiment that doesn't exist. You see, we would get this entire shaded region here. The existing microscope experiment would have been able to see all of this right here. But if you had even 1 millimeter of shielding, it only gets this little tiny area right here. And if you have any more shielding than that, you're just out of luck, okay? Now, a millimeter shielding, there are some other satellite experiments that for various reasons do have a millimeter size scale sort of shell around them. So it doesn't seem crazy, but I don't know. But I think that so it's pretty clear that the existing microscope experiment doesn't have any sensitivity.
So where are the
Yeah.
Bush type experiments in this plot here?
They're not there, okay? And the reason is that they are underground. So they have meters, well, they're in a basement. They have a building on top of them.
You can put that.
Yes, so I'm going to comment at the end. Yes, the Bush experiment yearns to breathe free, put it out into the open air. Okay, you probably want to put some plexiglass around it or something. But that seems like it might be doable, although, I don't know, Adelberger might yell at us. But they're not anyway that much more sensitive than this. So, but yes, I mean the atmosphere is a non-trivial thing, but the atmosphere is still less than like a millimeter of lead or something. Actually, no, you can figure it out. It's about a centimeter of lead or something, I think. Okay, so yeah, you could do a lot better, but it's in a building right now. That doesn't work. Okay, so the thing is, so this really doesn't have any, it's pretty clear, even without a lot of more detail, but this just shows you, also illustrates how important the shielding really is. If you can get rid of it, you can do so much better for the signal, right? Okay, and now there is a planned microscope 2, I think they call it Galileo Galilei. I don't know, it seems like maybe, I don't know, you don't want to be premature in naming something Galileo Galilei, I would say. But anyway, there is a planned microscope 2, and it is, it's I think in a more, it's not in a, I guess it's in a CDR stage, not a TDR stage is my impression. But if I take their numbers at face value, they can do a 2 order of magnitude improvement in the acceleration. So I do the same kind of plot, assuming different levels of shielding. Again, no shielding gets this entire region here. If I do something here, even if I do, even if I have 1 meter of shielding, I still get this little region here. So if nothing else, they should be able to get a slice of this. And they really should maybe, you know, if the experiment was designed for this better, maybe you could get closer to a centimeter or maybe even a millimeter. I don't know. Okay? So this is very much preliminary work, so a lot of things we don't know. I'm just telling you what we know so far. Okay, so just a few comments on future prospects. As I emphasized already, reducing the shielding improves the sensitivity a lot. So one thing you could imagine is if satellite experiments cared about this, I don't know if they will, but you could try to get them to reduce some of the shielding. And for example, I don't think it's completely nuts to add windows, right? If you wanted to let in the wind to your house, you open a window. You don't get rid of the whole house. And you could do the same thing here, right? It would make you don't literally have to open it up, but you could have some thin regions. You could have some directions where the dark matter wind can get in easier. Okay, so maybe you could get a millimeter that way by just having it in certain directions and rotating your satellite. I have no idea. Could you take these torsion balance experiments, which are an absolute sensitivity, have the best acceleration sensitivity? Could you get them out from these basements so that they have a chance? Okay, and that is an interesting question. These guys don't seem to be motivated to redo their experiments. They promise that they can do much better. This is the existing Bush experiment. I think they can do 1 or 2 order of magnitude better. So far, they haven't apparently been motivated to actually do it. Some other things that we have on our list to think about is that if you have these satellite experiments, they're going around the Earth, you can take advantage of the dark matter shadow from the Earth. You know that the dark matter wind will be off half the time, okay? So you'll have a very characteristic signal. I mean, that's probably more of a detail because you're never going to overcome, if you're just not sensitive to the acceleration, you're just not sensitive, right? And the number one thing on our to-do list at this point is really to make friends with experimentalists, to see whether, well, maybe they have some ideas too about other things that you can do with this. So yeah, that's my conclusion slide. So thank you very much.
Questions for Markus? Yeah.
So I was thinking, you started your talk with this Z2X portal, is that the name?
Yes.
But it seems that you can come up with several UV completions that give you the same phenomenon.
Absolutely.
So it's
Absolutely.
not so important.
No, it's not important. I just wanted to put that in because, well, I think that this is in this kind of very light dark matter community, that seems to be the sort of traditional way that people talk about these things. And I just wanted to say that it fits into that framework. But I actually agree with you. I just think in terms of F, I don't care where it comes from. That's the phenomenological parameter we're constraining.
Markus, in your plot, the very high cross-sections or couplings has been excluded from astrophysics and gravity tests.
Yes.
What exactly tests actually?
So one of them is just the star cooling that I talked about.
I see.
Okay, that just is a straight bound on 1 over F bigger than 10 to the minus 8 GeV inverse. And the other one, the gravity tests are just the one loop potential, which is an equivalence principle violating force. And if one were to plot it on this, it would be some jagged line that goes up and down, but it always is above this straight line. So it's nothing like a straight line at all, but it's always somewhere up here.
What I mean, what I have in mind is that if it's dark matter particle, well, with some mass, will it kind of also be interacting with the galactic plane in destroying it? If it's
oh yeah, I can tell you about that. So I can tell you that, for example, yes, we thought about this. It doesn't give you any, let me tell you an interesting fact, and you can tell me if you can find a way to probe this. You know that, so ordinary matter is rotating through the dark matter halo, okay? And so you can ask, okay, if I take an object that's rotating around the dark matter halo, it will be slowed down by there'll be a drag force. This is actually the first thing that we thought of when we thought about this, okay? And you can ask, well, are there any objects that would be stopped, that would be basically, so you really see the drag force, okay? And the answer is that it works for ordinary density objects, rocks, ice, but they have to be less than 5 centimeters if ever, okay? So if you can tell me some way that we know about 5 centimeter objects or less, okay. And now you can say, well, what about just the gas, okay? So the gas is just hydrogen and helium mostly, okay? But hydrogen and helium, now we don't get these big coherent effects, we just have ordinary scattering, right? And the mean free path for that is always much longer than the distance that it goes through the galactic halo.
I was thinking if dark matter would kind of, well, crossing a galactic disk and scattering on it, and if
yeah,
the mass
that's
of
what I'm
dark matter
talking
of the
about.
order of MeV or KeV, then it will destroy it, right?
Well, we can talk. Okay, I can tell you much. I think I'm happy to talk more about it, and I'd be very happy if we missed something. But we did think about that, and we could see no effect. These forces are tiny, and remember that since they go like the area, but of course the mass goes like the volume, so you get bigger acceleration for smaller objects. So that makes it very hard.
Okay.
Okay, but I'd be very happy to talk about it more.
Yes, so since probably you care more about the fine-tuning, so about the radial correction, I'm kind of confused. You do have the density to enter into the correction.
Oh yeah, so
but how about just a vacuum correction, like put a nucleon mass as power counting to?
Are you worried about naturalness?
Yes. Do you worry or not?
If you worry about naturalness, you should just not listen to my talk, because this model is extremely unnatural. So if I wanted to, I could have made a slide saying that maybe dark matter is anthropic, okay? But it's extremely so the natural region is way down here somewhere.
I think it's just one more step beyond that, which is is any correlation between your screening effect versus the fine-tuning problem here?
Well, only in the sense that it's natural in a region where the signal is incredibly small. Okay. I mean, I think that, I'm actually thinking a little bit about whether you could make a truly anthropic model in the sense that if usually we say that the misalignment mechanism is already anthropic because the initial value is not determined. But if I had some theory where the initial value of phi was pinned down by microscopic physics, then the mass could be varying anthropically. Okay, so I think it's possible that this kind of matter, this kind of dark matter could be just anthropic. It could be tuned from the point of view of fundamental physics, but it could just be anthropic. But if you really care about naturalness, yeah, you shouldn't be talking about, 10 to the minus 6 EV scalars probably, right?
More questions? Does this have an effect on your brain? Because they can okay.
It had an effect on my brain. But I don't know if I'll have effect on your brain. I don't know if you care enough about this.
Oh, maybe the shielding is good enough. I don't know. Okay.
I think I don't think you're not gonna be knocked over by this.
Jay, sorry.
So you have this background field that's oscillating, and it's coupled to the Higgs. So in essence, the Higgs Web is changing rapidly.
Exactly,
as a
and that's
function
where
of
this
time.
change. That's where the
And
mass of the nucleus.
So the mass of everything is going to be changing as a function of time.
Right.
So in principle, everything should be radiating gravity waves at this frequency. So
but
is it big enough to?
No,
it's not. Yeah, okay.
No.
Yeah.
I mean, and by the way, for the naturalness comment. I started this thing looking at higher interactions of a Goldstone boson because I had some taste, right? I wanted to do something natural, but those signals are always insanely small. I thought that maybe, coherent signals could overcome the fact that these are higher dimension operators and blah, blah, blah. No.
That's because of momentum dependence, right?
Yeah, just derivatives are really, really small when you're talking about, astrophysical things.
300
So you
kilometers
just,
per second.
so you just the realm of taste and this just don't overlap.
Okay, so let's thank Markus again.
Yes, thank you.
And we reconvene at 10 to 5. Time for coffee.
Yeah, coffee break. Hopefully Nathan didn't cut the coffee break. So Marcus,
Yeah.